right, so now we're going to look at the buoyancy force. Now, the buoyancy force is a type of force that is due to the pressure that is happening inside of some sort of fluid. The buoyancy of an object is the net upwards force exerted on an object that is submerged in a fluid. It is the net upwards force exerted on an object submerged in a fluid. Now that fluid could be air, that fluid could be water, it could be salt water, it could be oil, whatever. The symbol for the buoyant force is F with a subscript of B. Typically you see that as a capital B. And the units are, well, it's a force, so the units are newtons. Now when you have an object that is sitting in some fluid, you have pressure all around from pushing in all directions, all around your object. We know, though, at different locations, there is different amounts of pressure. So the further up you go, the less pressure you have. As you go further and further down, as the height or the depth increases, you have more and more pressure. So any object will have more pressure on the bottom of it than on the top. Because of that difference, that is going to give you your buoyant force. So, depending on the object, you can look at the density, the location, the gravity. All of this will affect the buoyancy. So we have a baseball bat. The buoyancy force, FB, is the force that is upwards due to the pressure of the fluid. And then the force of gravity is going to be due to the weight of the object pulling it down. So in here we have 3 different examples. We want to draw the force diagram of this, and we want to say what is going on with the forces, where is the net force, and which force is bigger, the buoyant force or the weight force. So in the first example, a rubber duck is initially floating in the pool, but a child submerges it underwater. So we know that it should be floating, but you push it down all the way down to the bottom. We know experimentally that this duck is going to want to almost immediately run back up to the top. So if we are drawing a free body diagram here, the buoyant force is going to be really high. The buoyant force is really high because the rubber duck has quite a bit of volume. The inside is mostly hollow, so it doesn't have much density. And we know that the density of an object is going to determine where it needs to be, if it rises or falls. So we have a pretty large buoyant force here. Now, the rubber duck is not weighed very much, and so the force of gravity is going to be a lot smaller. So if it wants to accelerate upwards, that means we must have a net force. The net force must be pointed up, which means that the buoyant force is greater than the force of gravity. Now for a rock is way more dense, and so thrown in the water, it immediately starts sinking. So we know that the density is going to be a lot higher for a rock. So because of this guy, he is going to start falling towards the ground. So what that means is that the buoyant force is not very big. And the weight of it, mass times gravity, is pretty strong. So in this situation, the buoyant force is much smaller than the force of gravity. We know that our net force is actually going to be pointed down, that it will accelerate down towards the ground. Not as much as it would if it was just falling through air or falling in a vacuum, but it will slow down just a little bit because of that buoyant force. Last one we have is a rubber duck that is not moving and floating on the water. If it's floating on the water, we know that the net force is 0. It's balanced. And so when we're dealing with our forces, that means that the buoyant force has to cancel with the force of gravity, because those are the only two forces acting on our little rubber duck. So this one has two equal forces. So the buoyant force would be equal to the force of gravity. So if an object is floating or suspended, if it's not moving, that means the forces must be balanced. Next concept we have is Archimedes' principle. So the classic story of Archimedes, who is a Greek mathematician, was called in by the king, and the king wanted him to verify that his crown was made of gold. And so Archimedes couldn't destroy the crown because that would be expensive, and obviously the king didn't want that. And so took the crown and submerged it in water and figured out what was its displacement. He used that to figure out what the density is, and he determined that the density was lower than pure gold. So then it must have some sort of silver mixture. And so when he is submerging this crown in this bath water, he was like, "Eureka! It is not actually gold." And so that's as the story goes. And so not actually true here, but the principle kind of stays the same. That you can submerge an object in water and you can use that to figure out what the density is. So in this scenario, every object is buoyed up, that's by the buoyancy force, by a force that is equal to the weight of the fluid that the object displaces. So if you take a container like this that is filled to the top and you drop a weight inside, that the weight, this mass, is going to displace a certain amount of volume. And the amount of volume that it displaces is equal to the volume of our object. And so we have these kind of two equations that we're going to use here. The first equation is the force of gravity. The weight of the object. That's going to be equal to the mass of the object times the acceleration due to gravity, mg. We also know that density, which is rho, is equal to mass divided by the volume. So if I want to write mass out in terms of these variables, the mass is the same as the density times the volume. Again, remember density, we use a rho, and volume, we use a capital V. So I can actually replace this equation, and I can replace the mass of the object by saying it is the density of the object times the volume of the object times the acceleration due to gravity. This is going to be the weight of the object. The second equation here that we're going to use is going to look at, use purple. It's going to look at the buoyant force. Now, the buoyant force is going to be essentially equal to the weight of the fluid that has been displaced. So if you look over here, if we know that this weight is 5 kilograms and you put it in this tub of water, when it is floating in this liquid, there's a buoyant force of 2 kilograms pulling this guy up. That means that 2 kilograms of water has been displaced here. If you look at the apparent weight of this object, apparent weight would be essentially like the normal force. The actual weight is 50 newtons. And if you put it in the water, and now this 50 newton mass, or this 50 newton weight here, is reading as 3 kilograms, that means that 3 times 10, 30 newtons is the apparent weight. Well, that 20 newtons has to go somewhere. So the amount of water that is displaced is 20 newtons worth of weight. That 20 newtons is equal to the buoyant force. There's 20 newtons of buoyant force going up. So for our second kind of equation here, the buoyant force, FB, is equal to the mass of the fluid times the gravity. So for this, we're going to have the density of the fluid times the volume of the fluid times G. Again, the buoyant force is based off of the displacement of the fluid, not necessarily the object. One other thing to note, that when the object is submerged, the volume of the fluid is equal to the volume of the object. Well, I said submerged. So when would that not be true? Well, it's not going to be submerged if it's only sitting halfway out. So if you think about an object, if you have an object that's sitting out like this, the buoyant force is going to be equal to the amount of displaced water. In that case, it would be only the part that is under the water that we would count towards the buoyant force. All right, next question here says, which of the following objects... Oh, let me write one more thing here. So the buoyant force, this is going to be our main equation that we're going to use here. The buoyant force is equal to the density of the fluid times the volume displaced times the acceleration due to gravity. That is our equation. So the buoyant force is equal to rho VG. But again, you got to understand what those variables are telling us. All right, now down here. Which of the objects shown would experience the largest buoyant force? Well, we know that the buoyant force is based off of the density, the volume displaced, and the acceleration due to gravity. And so all of these guys have the same exact volume here. The cork and all these objects are in the same exact place. So if we're dealing with the buoyant force, we are looking at the density of not the object, but the density of the fluid. These are all in exactly the same fluid, so that is constant. So that's going to stay the same. Then we have the volume. They are the same size, so that's going to stay the same. And the acceleration due to gravity, which is also going to be constant. We're on the same planet. So if all those variables are the same and they are all fully submerged, and that means that they should all have exactly the same buoyant force. Now, we know that these objects will behave differently because they have different densities, right? So they all have exactly the same buoyant force. Every single one of them has exactly the same upwards buoyant force. But if we're thinking about the weight of the object, a cork has very small amount of mass. The aluminum has a little bit more. And the lead has a ton. And so because of that, these guys have different weight forces. small, medium, and large. And so because they have different weight forces, we will experience different accelerations. Where this guy might have a net force that accelerates up, this guy might have one that's barely down, and this guy will have a huge one that goes down. So each one of these will experience a little bit different weight. And that's why we have the sinking and the floating. Last question, how would the buoyant force change if the objects were submerged in salt water instead of fresh water? Well, you actually have to look at the densities of each of these. We know that if you swim in the ocean, it's a lot easier to float. That means the density of salt water is going to be a little bit higher than the density of fresh water. If you look up this information, and you definitely don't have to memorize this, but salt water has a density of about 1,030 kilogram per meter squared, whereas fresh water, we've learned, is just 1,000. So if we're going to determine how this affects the buoyant force, well, the buoyant force is equal to the density of the fluid times the volume displaced times the gravity. So if you increase the density and you keep everything else the same, volume is the same, gravity is the same, that means that the buoyant force must increase. So it must, use blue here. The force of gravity, or the buoyant force, will increase. There's my answer. Alrighty.